This guide's going to focus on the LUT generation capabilities of ColourSpace, which are within the LUT Tools menu. In very simple terms, LUT generation takes a source and a destination and generates a 3D LUT to convert between the two. Pretty straightforward, but there are quite a number of options associated with that. In its simplest guise, you can use it to convert colour spaces. So let's say that we have Rec. 709 footage that we're going to display on a DCI P3 display, projector, monitor, whatever. So we are going to be working with a source that should be seen on a Rec. 709 monitor, but is going to be seen on a DCI P3 monitor. We can just call it test 1, and we have an option of different colour space conversion processes, and for technical LUTs like this, the most common use is peak luma, which maintains the luminance value irrespective of colour channel clipping. In this instance there won't be any because both are the same colour temperature, so the result when we create in this case a new LUT, because there is no existing LUT to burn it into. And there we go, 100% within target, and that is the generated 3D lookup table. There is a 1D view of it, but it's basically a small gamma change going from the 2.4 to the 2.6 of DCI P3. And we have a Granger image that we can see the LUT applied to. We can zoom in and turn on and off the LUT. We can actually change the LUT image, so if we wanted to apply it to a different image, let's say a different Granger or a video still or something, we can actually use our LUT manage to add a picture into the preview mode, which we'll just navigate here, and we'll just call up say a different colour ramp 3, which is a different form of Granger, and we can see there again the original image with the LUT applied. Keep that, the default Granger always stays there. So in very simple terms, that's the process associated with generating lookup tables. But if we were now going to generate a lookup table for calibration, and we've been working with this Chroma broadcast monitor, so we are now going to be working with a monitor that you want to be Rec. 709 because the source material that the monitor will be showing will be Rec. 709. But at the moment, the destination that those Rec. 709 images would be going to is our uncalibrated display. I know that can be a bit hard to get your head around, but it's a very logical approach once you understand the concept of source and destination. So we're going to use the Chroma probe matching active 21 cube 3, which is the large profile that was done when we were looking at profiling capabilities of ColourSpace. Now there are other options associated here which we'll come back to, but for this instance we're not going to use them because we have a large profile that was generated with a probe match. We are going to use drift compensation because we had that active, and we can see there are 186 drift patches within the profile, and again we can call it test 2 if you want, and we are just this time going to use peak chroma, and we're not going to use any of the other options at the moment, and we just hit create. And there we go, we have a conversion that reports 99% within target gamut. Now the reason that that's 99% and not 100 is because the display actually slightly clips blue. We can see that if we look at the lookup table, because we can see that there is blue being pushed against the edge of the LUT, because the LUT is trying to actually make more gamut, which it can't do. It's only a very small amount, but if we look at the actual profile itself, we can see where that is. And if we look at the probe match, there we go. Okay, if we look here, so we are targeting Rec 709. Just stick the luminance up there just to help. But if we zoom in to the blue, we can see that that is Rec 709, but the display, whilst it has a lot of blue, the blue is actually slightly too warm than the blue that we want. Again, if you imagine a line that goes from the white point straight through the blue of Rec 709 and extends out, that is effectively what we would rather have as larger gamut. What we've got is a blue that is obviously off target compared to the Rec 709 target. Not unusual and not a major issue, but it does mean that we can think about this a little differently. We could, when we make the LUT, choose to use disable gamut mapping. One of the things with standard gamut mapping process is it always tries to maintain a difference at the point at which the colours are clipping. That usually means that there is a change in luminance or hue or saturation. One of those or two of those three, or even all three, have to be changed for there to be a difference at the point of clipping. We can see that if we look carefully at the LUT image. We look at the blue, and if I enable disable the LUT, you may just make out that there is a patch in the middle of the blue where we are seeing it have what appears to be a change in saturation. In this instance, that's caused by the clipping of the blue. So if we disable gamut mapping and run another LUT generation, test 3, we'll use Peak Chroma again, create. This time it will create very quickly because there's a lot less processing going on in trying to work out the best processing to use for the gamut mapping. And there we go, still 99% coverage because nothing has changed there. But we do now have, if we center both LUTs, a little difference in the result. And if we look at the Granger image, zoom down, you can see the gamut mapping occurring, no gamut mapping, just a hard clip. Looking at some of the other options that we used making that LUT, we had drift compensation active. And drift compensation applies an offset throughout the entire LUT generation based on the drift data in the profile. If we look back at our profile again, okay, we can see that it actually says it has a drift with it as well. And looking at the drift graph, we can see that, yeah, there is certainly drift data. These were every 50 patches, and you can see that there is a form of cyclical drift in this particular display. It's very small, but it is there, and it is used as a compensation for LUT generation. In this instance, with that level of drift, the difference is going to be pretty small. We can show that, and if we just literally take our test 3, let's call that test 4, and again, this time no drift compensation, leave the gamut mapping disabled and create. There we go, 99 again, and if we now toggle between the two, you can see the very small difference, but it is a difference in the generation of the LUT. Okay, that brings us, I suppose, to hint. Hint is a process where we can use an existing profile to provide a hint to a new, smaller profile. Where this really comes into prime use is in manufacturing of displays, where you have a large batch of displays being manufactured at once. You can do a large 21 cube profile of one of the displays and then do smaller profiles of the other displays, but use the large profile to improve the granularity of the calibration on the other displays. So we'll just close down these LUTs, but just to make sure there's no confusion, we will clear those out from our library as well. And if we now call up the probe match, there we go, 5x3, we are going to hint it to the 21 cube 3, and we'll come back to augment, as that's yet another approach to improve the quality of the generated LUT. Augment specifically is aimed at grayscale, but can be used elsewhere. So anyway, now if we do test 5, we'll leave the disable gamut mapping on, but we're going to generate a lookup table initially. Let's do this, no hint, create. There we go. So that produces a result without the hint process, just using the 5cube3 profile. And if we now enable hint and go hint active, create. And there we go. And we can now compare the two results, and you can see that there is indeed a difference with the hint active. Which brings us on to augment. To understand augment, we really need to look back at the profiling side of ColourSpace. So we'll just kill out these LUTs. And look at the profile data. Now we have been working with the 5cube3 profile, which is a very small profile. There's not a huge amount of data in there. If we look at, there we go, we can see that it's a relatively sparse data set. And what we have also done is to profile a grey large also with the probe match. So this is just a grayscale only profile. So again, if we look at that in the, there we go. Okay, you can see that basically we have got a large set of grayscale data with just the RGB primaries in addition to that. And then with the existing 5cube3 profile, we can actually add to it the augmented data. So I've already done that here, but if we basically take the 5cube3 profile, modify, we can say add augment data to it, and we're going to add to it the grayscale probe matching active. Select that. We will call it test, so you can see it's different. Save. And now we have the 5cube3 profile with the augmented data applied to it. So you've now got a 5x3 cube profile, but added to that a large grey only profile. And when we generate the LUT, we can select disable hint. We will select our 5cube3 test, and it says that it has augmented data, and we can call that test 6 augment. And if we now disable augment and call it no aug, and again recreate the LUT, we can compare the two. And there we go. We now have a LUT generated without the augment data and with. And if you look, you can see in the LUT itself that the only thing that appears to change is in the center of the LUT, because it is the 1D data, the grayscale, that we augmented. And there you go. So with the aug data, without. So you can see there is actually quite a significant difference in having the additional grayscale data when we generate the LUT itself. When generating the LUTs, we have a selection of options in the actual process used, the algorithms within the colour engine. We've already mentioned peak luma, peak chroma. We have fit space, map space and hybrid as well. So we'll just clear out our existing LUTs. Peak chroma is the primary option to use because it's the most benign. By that I mean that it will take the profile data and very faithfully generate a LUT from it. What that can mean is if the display has issues or the probe has issues in reading that particular display, it can generate unwanted artifacts because they are inherent in the profile data. When that happens, the use of fit space, map space or hybrid can be preferential because they in different ways alter the data while doing the LUT generation. Fit space is a relatively simple process that effectively filters the data to look for underlying issues, to actually fit the profile itself into the kind of primary parameters of the profile data. Map space uses a dual step approach where rather than going straight from the profile to the source color space, it will actually do it in a number of steps so that you end up concatenating effectively different LUTs together to generate the final single one. Can be a very useful process, especially when the display is well under gamut compared to your target color space. Hybrid uses a totally different approach in that it will separate out the grayscale from the gamut and treat them independently, which can have quite a significant impact on the accuracy of the grayscale if the LUT itself, if the profile itself has any issues. So probably the best thing to do is to run some tests on these. So we'll go back to using our 21 cube profile with probe match. There we go. We're not going to use hint, we might as well put that back to none, and we'll leave augment off and we'll just call this back to test 1. So peak chroma, create. Okay, and we will very quickly just step to version 2, and this time we will do fit space, create, and then test 3, map space, and 4th, hybrid. Okay, and if we step between them, you can see that there are subtle but nevertheless visible differences in the generation of the LUTs. If we look at the 1D graphs, you can see that there is actually more of an issue, especially in the way it approaches the grayscale in the shadow area, with the peak chroma and hybrid being the closest, with fit space and map space again being relatively close to each other. The only way to obviously assess which of these is generating the better result would be to apply each LUT in turn to the display in question and run a verification profile, and see which one gives you the better results. With time and experience, you learn quite quickly which is the best for any given profile just by looking at the profile itself. The new LUT option does exactly what it says. With new LUT selected, it will always generate a new LUT. With apply to existing selected, it will concatenate the LUT defined here with the LUT that exists already within the tab. And lastly, we have the limit luminance. Very rarely used because these are nearly always set by the manual controls on a given display. Minimum luminance is usually the minimum the display does anyway. These values are extracted from the profile in destination. Max luminance is usually set directly by the display control, but can be set here if that control doesn't exist. The issue with this is that if you have an overly bright display, let's say 200-300 nits, and you want to bring it down to 100 nits, it will have no impact on the minimum, the black level. With a display, if you bring down the peak white manually with the display's control, it will bring down the blacks as well. If you use a LUT to do it, you can never reduce the blacks below what they are presently set to when the peak luminance is at its display's max of 300 nits, whatever it is. As with pretty much anything to do with the various options within ColourSpace, the Light Illusion website does have information that will help support these videos. In the case of what we're looking at with the LUT generation, at the moment it's in the historical guides as part of the LightSpace LUT management information. And if we go to the Convert ColourSpace, as it's known in LightSpace, we can see here that we have the, for example, the output options for generating the different LUTs, and you can see here it explains the difference between peak luma, peak chroma, fit space, and obviously has some more in-depth information there.